Okay, so a quick recap of the last lecture. So in the last lecture we talked about potentials. I started with a discussion on stability. We discussed when is an equilibrium position stable, and that was discussed in the context of understanding how the potential energy function looks like. Then we did a problem of teeter toy, which is an object where we have two masses placed symmetrically. It becomes stable in the position shown if the masses, the level of the masses are below the level of the pivot. I had made a mistake towards the end while writing the final result. So this has to be less than 0. So that small l cos alpha becomes greater than capital N. Then we talked about energy diagrams. We discussed the total energy for conservative systems being drawn as a straight line on the energy on this energy diagram, and this helps us understand whether the system is bounded or unbounded. So this system, for example, on the top is unbounded, because from the left side, if you draw E equal to constant line, it will hit the potential energy graph, but on the right side it is open. Similarly for this case as well. And then post that, we were starting a discussion on the frequency of oscillations. So we said that it's good that we know that a system is bounded, but then if a system is bounded, that means it will oscillate. If you give it, it's a conservative system, kinetic energy and potential energy will convert from one to the other. So if I give it some sort of a stretch and leave it, it will start to oscillate. So the next thing to figure out is what will be that frequency of oscillation for small amplitudes around the equilibrium position. That is very important in different parts of engineering, depending on the application, to know what the frequencies are. Okay, so we discussed that even though the potential energy graph could be any curve, could be any non-linear curve, but for small displacements around the equilibrium positions, we showed mathematically using Taylor series expansion that the oscillations will be harmonic. That is, the restoring force will have a nature of F equals minus Kx. You can either show that from the force ideas. Okay, the force can be non-linear, but for small displacements using Taylor expansion, you can show that the force will be linear, or you can do the Taylor expansion of the potential energy function. From that also, we had showed that it is of the form of half times Kx squared, where K is given as the second derivative of the potential energy curve about the equilibrium position. Okay, so that is where we stopped. So we'll continue from there. So for example, for a bounded system, such as this, where you have two masses m1 and m2 connected by a spring of spring constant K. So you can find the spring constant K if you know the potential energy curve of this connectivity. Oh, sorry, I've given you this. This is the model, and let's say the actual potential energy curve looks like this, which is typical for a diatomic molecule. If the energy is low, then we see that the system is bounded. So if you know this U function, you can calculate K. Remember, x naught is the equilibrium position, right? let's take this system that we have shown here, and let's try to calculate its frequency. I have my reference on the left hand side, so I measure x1 and x2 from there. So this allows me to write m1 times x1 double dot is equals k times x. Okay, so let's say x1 is, I mean, we have stretched the spring from the equilibrium position. So in that case, we see that m1 is being pulled to the right, because if the spring is stretched, it will pull m1 from left to right, and right hand side is the positive x direction. So this becomes, the force on this becomes k times, and the stretch in this case is x minus x naught. Okay, x naught is the equilibrium position of the spring, and you have stretched it such that it is now x. So this becomes k times x minus x naught. Now if for some reason your x was less than x naught, then the force will be, the spring is compressed. So that means mass m1 is getting a force to the left. Now for this case that we are thinking about, for the case where the spring is stretched, in that case, see m2. So m2 is being pulled to the left. m2 times x2 double dot becomes minus times k of x minus x naught. Right, so if I subtract the two equations, dividing each one first by their masses, so this is what we get. Now remember, we are trying to find the oscillation frequency here, right? And k I already know. K I know from my potential energy graph. It's a second derivative around the at the equilibrium position. Now we already have seen this in the topic on collision, that this 1 by mu is 1 by m1 plus 1 by m2, where mu is called the reduced mass. So we can see from this case that this is, what is the frequency here? Square root k by m, simple harmonic system, oscillator. And k again, I mean, in this case, our m is actually the reduced mass, as we can see from this equation. Is that clear? So we started with a system of two masses connected by a spring. The masses were different, and we see that if I mean it's like two particles connected with each other through a spring, and what we notice is what we calculated is this frequency of oscillation is square root k by mu, and there's no I mean the masses are different, and that mu, the reduced mass, is given as this, right from simple Newton's second law. All right. Now there are situations where your potential energy graph is more conveniently written in terms of an angle theta. We discussed pendulum. So in that case, we had described the potential energy as a function of theta. So in this case, our u had come out to be mgl times 1 minus cos theta. And if you take this theta to be small, because remember we are talking about small displacements around the equilibrium position. In that case, we get a situation where it behaves like a simple harmonic oscillator. Right? The force is almost linear. So in that case, if theta is small, you can use the expansion of cos theta with only the first term. So this gives us mgl times theta squared by 2. One minus cos theta. So 1 minus cos theta is 1 minus theta squared by 2, and so on. So 1 minus cos theta, the first term is minus theta squared by 2. So that's we'll put an approximate sign here, because for small theta this is an approximate. There are other terms, but they are so small that we have neglected them. Similarly, the kinetic energy as a function of theta is half times m L squared times theta dot square. You can see for this situation, I mean there is no r dot, there is only theta dot in this case, because the rod is of fixed length L. So I'm not trying to solve a problem here, I'm just trying to show you that there are situations where it's more convenient to write potential and kinetic energies as a function of theta, not length or displacement. In that case, if we write more generally, we represent some variable q. Okay, it could be angle, it could be displacement, it could be something else completely. And your kinetic energy will be written as a function of q dot. So the total energy in this case is u plus k, and we know it's a conservative system. These are the kind of systems we're talking about. We'll start a discussion today on systems where energy will be lost. Till now there is no friction, but in real situation, if you take a pendulum, you displace it and leave it, after some time it stops. So we will talk about those systems as well. Those are called damped systems, but for now we are talking about undamped systems, or systems which have only conservative forces acting. So in this case, dE by dt is 0. Total energy remains constant. So if you do that, if you expand this further, this gives you an equation of the type of this. Okay, and this equation is very similar to the equation we had for a restoring force system, where F was equal to minus kx. And I'm sure you have solved second order ODEs in your engineering mathematics course, right? You know how to solve this system. So this actually is very similar to what we already have done, and the frequency of oscillation is square root A by B. Is that clear? So for those who are just joining, we're talking about the frequency of oscillation of systems connected, which are bounded. Of course, unbounded systems will not have any frequency associated, or the frequency will be 0. Right. I asked you to solve the problem yourself of the theta toy. We discussed the theta toy problem and showed that it is stable if the two masses are below the pivot level. Now the question was, okay, it is stable, but what is the frequency of oscillation? So I will not solve the problem, it's already there in the book. What we see is that the frequency of oscillation for the theta toy in this case, the variable S is coming from geometry. S is the distance from one mass to the pivot. Now we also saw last time that S cos alpha should be greater than L. Sorry, L cos alpha should be greater than L, capital L. And we can see that if small l cos alpha minus L is greater than L, then we have a frequency associated with that. Now what happens when small l cos alpha gets closer to capital L? The frequency reduces, right? When small l cos alpha is close to capital L, that means the masses are at a level which is very close to pivot. So we see from this relation for the frequency that the frequency is small for that situation. Okay, and it makes sense because we're talking about a weak restoring force. The restoring force is very large if your small masses are very low because the stability is very high. But as your small masses move up, you see that the restoring force becomes weaker and weaker and the frequency of oscillation becomes smaller or the time period becomes larger. And the system becomes is getting to the threshold of stability. So we have some idea now that if the frequency is high, if the oscillation frequency is very high, then we are towards stability. As the oscillation frequencies get smaller and smaller, the time period gets larger and larger, we are getting towards the threshold of stability, not instability, but threshold of stability, right? And this is what happens in ships. So when ships are designed, for the people sitting inside, if the frequency of oscillation is very large, it's very uncomfortable. Imagine a small bump and you start oscillating very fast. It's not very comfortable for the people inside. But the system is stable. Now if you want it to be more comfortable for the people inside, if somebody who's designing the ship purely cares about the ergonomics, or not ergonomics, but the comfort, and has no idea about stability, they will end up designing it such that the oscillation frequency is very small. But then what happens is, the ship may topple. Okay? So there is a trade-off between frequency and stability. Larger frequencies are highly stable and smaller frequencies are close to the threshold of stability. Okay, so this ends our discussion on the potential ideas, but we will continue the discussion through harmonic oscillators. Any questions? So now that we have talked so much about harmonic oscillators, let's discuss it in detail. In the book, it is a separate chapter, but for us, the discussion is almost continuous. Now, what are the two new things we'll discuss in this topic? The first is damping or friction. So we have talked about masses of this kind with a spring, but what if there is friction on the ground? What if there is friction because of air? All these situations are very common. So in that case, we'll have to add a separate term in the force, and the OD becomes a little bit more complicated. The second case is forcing. Now the forcing is something which we haven't discussed yet. So till now we are talking about free systems, in the sense that there is no external force being applied. The forces are only internal in nature. So if we have external forces that we are calling forcing, then we have to figure out what will be the nature of the motion of the system, because that is what you typically do. If a system is oscillating and you want it to oscillate, but it is losing energy because of friction, you have to constantly feed energy. Now that constant feeding can be a constant force, or it can be a force which is periodic, that is, it's a function of time. So we have to figure out, or we have to model the system so that we can predict its motion, given it's going through constant or continuous forcing and is also losing energy because of friction. So we'll discuss this as a part of this discussion on harmonic oscillators. Now we'll need one more lecture, but I have some demonstration for you today. So for that, we'll quickly wrap up with the first topic, which is simply a recap of what we have done, but just discussing some terminology. Can I request some silence, please? As I said, if you want to discuss, you can feel free to go out and talk about it. Or if you really want to talk in the class, you use your phones to chat on a silent mode, but please do not talk, it is distracting. So if it's a frictionless harmonic oscillator without any external forcing, F is equal to minus kx and F is equal to mass times the acceleration. So that gives us mx double dot plus, there is no term for x dot, plus kx is equal to 0. I hope I made myself clear that please do not talk. It's a very well designed acoustic room, it's very distracting. I can hear you. You don't realize that while you're talking, but I can still hear you. If you really want to talk, you can go out and talk. I have no problems with that. Plus, please do not distract the class. So this has a solution which is of the type d sine omega naught t plus c cos omega naught t. We will call this 1. Again, I hope you have done this in your engineering mathematics course. You've done this, right? Converting to a characteristic equation and so on. Okay. So in this case, the frequency that the omega naught that we have is square root k by m, that we already have discussed, and this is called the natural frequency of the oscillator. There is another way we write the solution. X is a function of time. Remember, there are two constants of integration here. Omega naught is not a constant; it's just a variable. It's just an expression in terms of k by m. B and C are constants of integration because it's a second order ODE. So that should give us two constants of integration. These are B and C. There's another way to write this. Again, we have learned this in the topic on waves. So we write it in terms of a single cos, and again we can do that if we expand cos, use the relation of cos alpha plus beta and expand it. So we can find out, we can write this in terms of a single cos wave with a phase phi. The amplitude is A. So whichever style you like, we use number 2 mostly. So you can go from one to the other. So A cos phi becomes C, and A sine phi becomes minus. So if I know A and phi, I can find C and B, and if I know B and C, I can find A and phi. The time period in this case is 2 pi by omega naught, and the frequency in hertz or cycles per second is omega naught upon 2 pi. Omega naught is the circular frequency, or in radians per second, and number of cycles, or a number of cycles per second, or hertz, is omega naught by 2 pi. Now from the energy side, system constantly exchanges potential energy with kinetic energy. So the potential energy is half kx squared. Now x is a function of time, so I can write this as x is a function of time squared. So we just now wrote x as a cos omega naught t plus phi. So this will help us find out the potential energy at any given time rather than any given position. Now if I know the time, I can substitute that here, and that gives me what is the energy of the system at that time. Kinetic energy is half mv squared, and v can be written as x dot. Okay, so x is a cos omega naught t plus phi. So you differentiate that, you get x dot. Take a square. So what that gives us is half times m, and then v squared becomes omega naught squared a squared. Then we have a sine instead of a cos because we differentiated x. And omega naught, remember, was omega naught square was k by m. So I can write m in terms of k and omega naught. So this simply gives us half k square a square sine square omega naught t plus phi. So we are expressing u and k in terms of time now instead of position. Total energy in this case is constant. Let's see. You add them. So what we see is should it be a k? Right. So total energy is u plus k, and u is half times ka squared times cos square of this angle, and sine is half times ka squared plus times sine squared of the angle. So if you add them, sine square plus cos square becomes 1. So this becomes half k a squared, and which is constant because the only forces acting in this case are conservative forces. Right, before I move on, I would want to talk about the idea of time averaging. So let's say we have a function. So this is a completely independent topic of mathematics. So let's say we have a function f as a function of time, and I want to find out the time average value. We denote that by an operator f in angle brackets, and we define it as 1 upon t2 minus t1 times integral of ft dt from t1 to t2. So what we are doing is we are taking the area under the curve between t1 and t2 and dividing that by the interval t2 minus t1. Okay, so this is the time average value. The analogy is if you are filling a bucket with a pipe that's pipe that is feeding in water to the bucket. Now the flow rate or the velocity of the water coming out of the pipe can be variable with time. Okay, so that velocity as a function of time is ft, and the amount of water that gets filled in the bucket is the area under the curve. Either you can have a variable situation, or you can get the same area if you have a constant flow rate of water, that is the velocity was constant for the same time. So this time averaging basically means that we are approximating that changing function as a constant function, so that the area remains the same, or whatever that area means in the problem remains the same. So for the bucket problem, the amount of water that gets delivered is the same. So the average time average value of the function is simply a constant value throughout the time interval. So what is, well, a problem for you? If ft is simply sine omega naught t, and we are talking about one full wave here, so from 0 to 2 pi. So what is the time average value of this function? 0. You can see that graphically as well, right? So, or we can write sine omega naught t, time average is 0. What about sine square omega naught t? In a full wave, let us say 0 to 2 pi. One by, or let us say, well, let us make it just theta, or sine square t. 1 by 2, right? What about cos square t? Same? Good. So you understand that. This I think you have already done as a part of alternate currents, right? Okay. Good. So we understand this operator now. So let's find out the time average value of the potential energy curve or the potential energy function. So potential energy was half k a squared cos squared omega naught t plus phi. We are taking this, and what is one cycle? One cycle is from 0 to time period, whatever the time period is. So what this becomes half time 1 by 4 times k squared, and kinetic energy also becomes the time average value of kinetic energy also becomes half times k squared. So we can conclude for this particular situation that the time average potential energy and kinetic energy are equal. Is that right? That will not be the case for damped oscillators, as we will see next time. This conclusion is only drawn for the current situation, which is for undamped harmonic oscillators. Now I will not solve the problem because that requires some mathematical work. I will simply pose the problem here before I show that demo. Now damping requires us to define what kind of damping we have. So till now in the system we have the net force acting on the system was minus kx, but this time we also have a force because of friction. Okay. Now we know that the friction force will act against the direction of motion, so that will also have some minus sign, but what is its nature? So the most common, does anyone know or I mean, we have solved problems of friction. Does anyone remember the model for friction that we use typically? So restoring force is proportional to displacement. What will friction be proportional to? Velocity, right? If the body is not moving at all, there is no friction. The friction is because of its movement. The faster it moves, the intuition is the more friction it will experience. So the model of friction we will use is minus a constant b times velocity. So I replace this friction force with minus a constant times the velocity. Okay. I'm just talking about that right now. So this constant, now this model is typically called a viscous drag model or the viscous friction model. There are other models as well, but this one is the most common one, and it doesn't even work, doesn't just work for mechanical systems, it also works for analogous systems in, for example, electrical system. So resistance or the resistance times the resistivity times the current, V equals IR. What was I? Current was the first derivative of charge. Similarly, velocity is the first derivative of position. So you see that these analogous systems, they are very similar. So the mathematical model will be exactly the same, and so the output or the interpretations we have or the analysis we will do for the system, this mechanical system, will be equally valid for electrical oscillators as well, or there are other kinds of oscillators we experience in different domains of engineering. They will be. So this model is not simply applicable for mechanical systems. So this is called, so you will see electrical systems, we have used a viscous friction or viscous resistance model and so on. So this is the same as, but the idea of viscosity comes from mechanical systems where you have air or a liquid. So you can think of this system immersed in some liquid, just to exaggerate the effect of fluid, although air will also have some drag associated, but that will be very small. It will only become significant for large velocity. So if you want to have a drag, a significant drag for lower speeds as well, then you can put it in a liquid which has high viscosity. Okay. So this viscosity is a property of fluid or the geometry of the solid and so on, but that is something we don't worry about that right now. So what's the equation we have? So mass times acceleration, that is the force, is minus kx, that's a spring force, and minus bv, that is your friction force. So this is the ordinary differential equation that is associated with this problem. Have you solved this problem? Have we solved this using the ideas of complex functions? Have we done that? I need a yes or no. I mean, if it's a yes, I will not discuss this at all, but if it's a no, then I'll want to discuss this. No? Okay. Because you get different situations, the solution, depending on the sign of the discriminant or the characteristic equation, you will get either a damped system, an over damped system. So this system, in some situations, if you are let's say the damping constant B is very large, extremely highly viscous fluid, then the solution you get is non-oscillatory. You see that you pull it and leave it, it just goes to 0, okay, or asymptotes to 0. x is a function of time. That's what I'm talking about. Now, if the damping is lower than a critical damping value, then the system shows this behavior, but the amplitude reduces. So, you pull it and leave it, it will still oscillate, but the amplitude reduces to 0. So, there is a critical value of B, or basically critical value of B versus K, that results in either an underdamped system or an overdamped system. So, these ideas can be best understood from the solution of the equation that we have here. So, that requires us to solve this using the ideas of complex numbers. So, I will discuss it in the next class, but I want to show you a demo. Till now you must have thought about, see, what is the use of all this? This is a very simple first level mechanics. I mean, okay, we use it for understanding or developing fundamentals, and once the fundamentals are developed, we can then learn advanced ideas, which could be anything from advanced dynamics to robotics, or even advanced ideas of physics or other sorts of engineering. But these ideas, these very basic ideas of mechanics are directly applicable to research problems that we solve nowadays for a field called particulate mechanics. So, let me show you a demo of what we actually do in lab.